Hello, this video is going to discuss how to compute the periods of planetary orbits using Kepler's third law. For this, we will need to describe Kepler's third law and draw an ellipse and discuss a few terms, and then the calculations themselves are fairly trivial, but we'll go through it. This is an introductory lesson on celestial mechanics, and I'm taking the information for this tutorial from a book that I just received in the mail called The Fundamentals of Celestial Mechanics by Danby. Very neat book. If I open the book up to page 5 and remove the laurel leaf that is on that page, I find that Kepler's third law is listed here as the squares of the periods of any two planets are in the same proportion as the cubes of their mean distances from the Sun. Well, if you're like me, you have absolutely no idea what that means. But let's take a formula that's given right here. It says p squared equals a cubed. All right, let's use that and see if we can't compute the orbital periods of the planets in our solar system. So first, we need to construct a model of a planet orbiting the Sun before we look at formulas. And one way to do it is to just freehand an oval, but I thought, given this channel's penchant for sacred geometry, we would use some sacred geometry to construct a simple oval. Here's how you do it. Just create about a 1-inch radius, and then bound two circles together where they only have one point that touches. So you'll want your next circle to touch at the center or at the edge at just one tangent point of the previous circle. Let me just move my point. All right. This will give us a good enough approximation of an oval. Okay. So let me darken in the center points of those circles there. And then using a straight edge, we'll just freehand a construction line right through softly. Now, if you set your compass point on the edge of the circle and expand it to the diameter, then place your compass point in the center of the circle. Make a little mark up here and a little mark down there. Do the same thing on the other circle, making another little mark. Right? And then swing this back around, back to the point at the edge of the first circle, and expand the radius of your compass to be essentially 1.5 diameters or 3 radii. And then place the point of your compass at the intersection of those two little marks that you made. If we're careful, we will construct an oval or an ellipse, and we can fill it in. So here's the top of the ellipse, and then the bottom of the ellipse is here. All right, and then what we'll do is erase all of the little marks in between because we don't need them. We were just really trying to get an ellipse. So just erase those other marks because all you really need is the ellipse itself. No need to confuse ourselves. Okay, now I'll just take a moment to kind of darken in this line here and make some final erasures. This is not an accurate model of a planetary orbit around the sun, but I thought it was fun to use the sacred geometry to make the ellipse. Let me not destroy my work with this freehand, but we'll just darken in the orbital path a little bit. Yep, that's what I was afraid of. That'll work as an orbit. So we'll place the sun here. All right, I'll draw it in with an orange color so we know it's the sun. Even though the sun is actually white, well, we see it through our atmosphere as yellow or orange. So we'll just represent it that way. And then we will calculate first the orbital period of Mars. So we'll put Mars somewhere. We'll put Mars here. This will be Mars orbiting the sun. Mars is the red planet, so this will be Mars. And this will be the sun. Now we have to introduce a few terms. This distance from the sun to the orbit right there, this shorter distance is called the periapse. Or maybe actually I think it's more correct to say this point right here, not that distance itself, but that point where the orbit is closest to the sun is called the periapse, and the point where the orbit is farthest from the sun is called the apoapse. All right. These two distances the periapse and the apoapse distances together form what's called the semimajor axis. The problem with an elliptical orbit is that the radius changes constantly. So it's not like a circle. You can still see the faint outline of the circle we used. The circle has a constant radius. Wherever you draw the radius in a circle, that radius is constant. But in an ellipse, the distance from this point to here is different than the distance from this point to here, and it changes constantly. But this whole axis right here is called the semimajor axis. That's the semimajor axis. And that is denoted by the letter A. Okay, so whenever you see A, that's the semimajor axis. The semimajor axis is measured in astronomical units. Measured in astronomical units. Okay, now one astronomical unit, and this is AU for astronomical units. One astronomical unit, or 1 AU, is the distance from the Earth to the Sun. All right, that'll just be a little sidebar. All right, I think we're ready to compute some of the periods or orbits for the planets. And like I said, we'll start with Mars. So back to this book for just a moment. This book shows us that according to Kepler's third law, and see, I'm just going to skip this. The sidereal period of a planet can be calculated from its mean synodic period. I have no idea. But I know that it says here that the sidereal year can be calculated as p squared equals a cubed. The period right here, squared, so the period is the time in years squared of the planet orbiting the sun, is equal to the cube of the semimajor axis. So let's put the fundamentals of celestial mechanics away for just a moment. And if I shift onto the internet and look up the orbital properties of planets, which I found on astronomynotes.com under their planetary table link, I find that the semimajor axis of Mars is 1.524 astronomical units. So let's make a little table here. The semimajor axis of Mars. So we'll do Mars and then its semimajor axis or A was equal to 1.524 astronomical units. Okay, fair enough. Well, let's take a look at the formula and see if we have enough information to proceed. The period squared, this is according to Kepler's third law, is equal to the semimajor axis cubed. Okay, so if I want to just find the period in years, this is the period in years. I just take the square root of both sides, right? And so I'll end up with the period in years is equal to the square root of the cube of the semimajor axis for the orbiting body. So let's do for Mars. And since Mars is red, we'll do it in red. So the period squared for Mars is equal to the semimajor axis for Mars cubed. Well, we know this. We know the semimajor axis, or this whole distance right here, for Mars, from the periapse to the apoapse for Mars, is equal to 1.524 astronomical units. So we'll plug in 1.524 AU cubed, and that is equal to the squared of the period. So if I want to just find the period, I'll write P Mars equals the square root of the cube of the semimajor axis, which is just A cubed. Okay, so what I'll do is take a simple calculator, put 1.524 times 1.524 times 1.524 equals 3.5396058. That is the cube of the semimajor axis for Mars. So if I want to find the square root of that, I just hit my square root function, and I find that the period in years for Mars is equal to 1.88 years. Okay, and that's relative to Earth years. So this is the period for Mars is equal to 1.88 years. So in Earth years, it takes Mars 1.88 years to orbit the Sun. Well, that makes sense because Mars is farther away from the Sun. So we would assume that its orbit would take longer. So what we'll and put in our table over here, suppose I should have put Mars right here in our table. And then we'll put planet right here. And then we'll create another column called period. And we found that if the semi-major axis is 1.524 astronomical units, the period is 1.88 years. And this is in years. Well, why stop there? Let's continue and see if we can't find the orbital period for other celestial bodies. Let's take the semi-major axis for Mercury, which is the planet closest to the Sun. I'll make a new row. This one will be for Mercury. So since Mercury is closer to the Sun, we would expect that its semi-major axis would be less than Mars and less than Earth's. And indeed it is. The semi-major axis for Mercury is 0.387 astronomical units. Okay. Well, I don't know what color to use for Mercury, so I'll just use blue. The period for Mercury would be equal to the square root of the cube of the semi-major axis for Mercury. So that would be 0.387 AU cubed. So we'll just go back to our calculator, and first we'll cube the semi-major axis for Mercury, 0.387 times 0.387 times 0.387, and that gives us 0.05796. Let's take the square root of that, and we find that the square root of that is 0.2407. So the period for Mercury in years is 0.24. How many significant digits did I use? 4. 0.2408. And this is years. So we'll put that in our table. 0.2408. And let's continue. We'll now do Venus. Venus has a semi-major axis of 0.723 astronomical units. And if I use this green color here, the period for Venus is equal to the square root of the cube of the semi-major axis for Venus, which is 0.723 astronomical units. 0.723 astronomical units cubed. So we'll take 0.723 times 0.723 times 0.723, and then we'll take the square root of that, and that gives us a period of 0.6147, or the significant digit is 0.6148. 0.6148 years. Okay, so we'll plug that back into our table. 0.6148. Just to make sure that we're doing this correctly and that Kepler is right, this was from Kepler's third law, I should say. That was the P2 equals A3, or P squared equals A cubed, I should say. Let's do Earth. Let's make sure this actually works. So this is Earth. Earth is 1 astronomical unit. So if we plug Earth into our equation, and for Earth we'll use blue, because Carl Sagan called Earth the pale blue dot. We'll use Earth. I'll try to make some space here. We'll say the period for Earth is equal to the square root of the cube of the semi-major axis for Earth, which is 1 astronomical unit cubed. All right, just to prove the point, 1 times 1 times 1 is equal to 1. And then if I take the square root of 1, I get 1. So the period of Earth is 1 year. Okay, well, thank goodness that that's true, because it is in fact 1 year. Okay, it's exactly 1 year. Now let's look at a planet that's farther away. Let's look at Jupiter. I'm going to stop with the calculations because we're understanding what we're doing here. I'll just do it over here because I'm going to run out of space. What is the semi-major axis for Jupiter? Well, it's 5.203. The semi-major axis for Jupiter is 5.203 astronomical units. So if I cube that, 5.203 times 5.203 times 5.203, and then I take the square root, I get the period for Jupiter as 11.87 years. Now that's interesting. It takes Jupiter 11 Earth year, 11.87, almost 12 Earth years to orbit the Sun. So the Earth will orbit the Sun 11.87 times, almost 12 times, in the time that it takes for Jupiter to orbit the Sun one time. So let's take it really far out, and let's look at Neptune. I'll leave the rest of them for you to calculate so I don't spoil all the fun. So the semi-major axis for Neptune is 30.069. Okay, 30.069 astronomical units. So if the semi-major axis, the distance from the periapse to the apoapse of Neptune, is 30.069 astronomical units, then what is the period in years of Neptune's celestial orbit around the Sun? Well, 30.069 times 30.069 times 30.069 equals this enormous number. And if I take the square root of that, I see that it takes 164.9 years for Neptune to orbit the Sun. So the Earth will orbit the Sun almost 165 times by the time it takes Neptune to orbit the Sun once. Think about it like that. That's pretty crazy. So this is far, far out. The normal model that we see of the solar system, where all the planets are stacked together, is ridiculous, because now you see the different distances. The semi-major axes for the various planets are much different, and they jump far, 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 far. So there is one cool trick that I saw in this book that I'll show you before we close. If I go back to this page, I noticed this cool thing at the bottom of the page. It said Bode's law. Consider the sequence of numbers 0, 3, 6, 12, etc., where after the start, each number is doubled to give the next one. Add 4 to each and divide the result by 10. So I had 0, 3, 6, 12. Let me make this 0, 3, 6, 12. We'll do 24 and 48. And it said add 4 to each and divide by 10. So this will be our original column, and then this will be the plus 4 column, and this will be the divide by 10 column. So this is the original column, the 4 column, and then the divide by 10 column. All right, so let's take a look at this. We'll see what it gives us. I think it might give us something interesting. So first, we'll do 4. So this is 4, and this is 7, and this is 10, and this is 16, and this is 28, and this is 52, and we'll just go, maybe we'll go another 2. 96, and then 96 times 2 is 192. So 96 plus 4 is 100, and then 196. All right, now we'll divide by 10. So this is 0.4. Divide by 10, 0.7. Divide by 10, 1. Divide by 10, 1.6. Divide by 10, 2.8. Divide by 10, 5.2. Divide by 10, 10. Divide by 10, 19.6. What are we finding? What is this? What's going on here? Well, if I look at the semi-major axis for Mercury, it's close to 0.4. All right. If I look at the semi-major axis for Venus, it's close to 0.7. If I look at the semi-major axis for Earth, it's 1. Right? Then I skipped some, then I kind of jumped around. So 1.6 is close to the semi-major axis for Mars. What was my next calculation? Jupiter. Look, 5.2, very close to the semi-major axis of Jupiter. And then the last one I did was Neptune. I guess I would need to go one more distance. So let's see, 192. Times 2 is 384. And then if I divide that, or if I add 4 to that and divide by 10, I get 38.8. How did I mess that up? Well, anyway, the point of Bode's law is that this is called Bode's law, by the way. This is Bode's law. And it's not an exact match, but it's interesting that just doing that little sequence, adding 4 and dividing by 10 gives us a very close approximation of the semi-major axes of the planetary orbits in our solar system. So in this tutorial, we used Kepler's third law to compute the periods in years of the orbits of several planets. So I hope this was interesting. The celestial mechanics topic is really a fascinating one to me. And I hope to do more videos on this in the future. So remember to please like and subscribe. Thank you very much.